All right, today we're going to totally flip what you think you know about vectors. We're going to see that they are so much more than just little arrows floating around in space. Let's dive in.
So, when I say the word vector, what's the very first thing that pops into your head? Seriously, just take a second and picture it.
Yeah, I'm guessing it's something that looks a lot like this, right? An arrow. It's got a certain length, we call that magnitude, and it's pointing in a very specific direction. Now, this is the classic definition you probably learned in physics class, and look, it's a great starting point, but it's definitely not the whole story.
Okay, but get this. What if I told you that a function, like a of x, could also be a vector? Or that just a simple stack of numbers could be one too? That sounds kind of weird, doesn't it? An arrow has this clear physical shape, but a function is just a rule. How on earth can you be the same kind of thing? Well, to really get to the bottom of this, we have to change our thinking. We need to stop focusing on what vectors are and start looking at what they do. It all comes down to a set of rules.
You see, this is the crucial idea right here. We're shifting from a visual definition, it's an arrow, to a behavioral one. An object gets to be called a vector if it just plays by a specific set of rules inside its group, which mathematicians call a vector space.
And you know what? The rules are actually super simple. It really just boils down to two things. First, you have to be able to take any two things in your set, add them together, and get another thing of the exact same kind. Second, you have to be able to take any one of those things and multiply it by a number. We call that a scalar, and again, you get something of the same kind back. If your collection of objects can do those two things, that's it. Congratulations, you've got yourself a vector space, and everything inside it is officially a vector.
All right, let's put this new idea to the test with our first, kind of surprising example. Can a function really be a vector? Let's take a look. Okay, so we're looking at something called continuous complex valued functions. Now, don't let the fancy name scare you off. All that really matters for us is that they're a set of well-behaved functions. The key thing is that they can be added together and multiplied by complex numbers, which are just numbers that have both a real part and an imaginary part. So let's check this against our rules. Can you add two functions, say a of x and b of x? Yep, and you just get a new function c of x. Can you multiply a function by a number to, scale it? Of course. Well, since they play by both rules, boom, this set of functions forms a vector space. That means every single one of those functions is, by definition, a vector. How cool is that? All right, I know that was a little bit out there, so let's bring it back to something a bit more concrete that you can really picture. Let's talk about column vectors. This might look a little more familiar, and it's the perfect way to see our rules in action. A two-dimensional column vector is really just a list, a stack, if you will, of two numbers. In this case, they're two complex numbers we're calling alpha 1 and alpha 2. And those numbers? They're just the components of the vector. That's it. Just an ordered pair of numbers written one on top of the other. Okay, so let's check rule number 1, addition. It's exactly as straightforward as you think. You take two of these column vectors and you just add the matching parts, the top number with the top number and the bottom number with the bottom number. And what do you get? A brand new column vector. So, rule 1, check. And what about rule 2, multiplying by a number? You guessed it, same basic idea. You take one column vector and some number, we'll call it z, and you just multiply each component inside the stack by z. The result is a new scaled up or scaled down column vector. So rule 2 is satisfied, and that makes these stacks of numbers officially vectors. And this is where it gets really powerful. We don't have to stop at two components. You could have a column vector with 5 numbers, or 100, or 1,000,000. As long as you define addition and multiplication in this component by component way, you've got a totally valid vector space. Okay, let's pull all these threads together. By shifting our focus from what a vector looks like to what it does, we've unlocked a much bigger, more powerful way of seeing the world. There's this quote from the source material that just nails it. The whole idea of a vector space is this massive generalization. That arrow we all know and love, it's just one tiny example from one particular vector space. It's not the only game in town, not by a long shot. So let's look at the big shift in thinking here, side by side. We came in with the old idea, a vector is an arrow in space. We're leaving with this new, much more powerful idea. A vector is any object that belongs to a group where you can add them together and multiply them by numbers. It's not about what it is, it's about what it does.
And that really leaves us with a pretty cool question to chew on. If something as abstract as a function can behave like a vector, and something as simple as a list of numbers can too, what else is out there? What other things in math, or maybe even in the real world, are secretly vectors, just waiting for us to see them for what they truly are? Thanks for watching.
All right, let's dive in. Today, we're jumping headfirst into the weird and wonderful world of quantum mechanics to unpack one of its most essential tools, the strange but really powerful language of bracket notation.
You know, the second you crack open a quantum physics textbook, you're hit with these words, bras and Kets. Honestly, it sounds more like a department store than cutting-edge science. So what's the deal with these bizarre names? Well, that's exactly the mystery we're going to solve. So to really get to the bottom of bras and Kets, we actually have to take one step back and talk about a really fundamental idea in math that makes this whole system work. And that idea is called duality.
Let's start with something you probably remember from math class: complex numbers. You take any complex number, we'll just call it z, and it has this kind of shadow version, or a dual version, called its complex conjugate, which we write as z star. They're two different things, but they're totally fundamentally linked. Just tuck that idea away for a second.
Okay, now here is the really crucial leap. This idea of a dual version isn't just some cute trick for numbers. Oh no, it's a really powerful concept that you can scale way up, all the way to the complex vector spaces that are literally the backbone of quantum mechanics. They also have their own dual version.
And this is where we finally meet our main characters. In quantum mechanics, our main vector is called a ket. It's written with that vertical bar and the right pointing angle bracket. And just like our number z at its conjugate, z star, every single ket has its own matching vector in that dual space. And what do we call that one? You guessed it, the bra, which is written with the angle bracket pointing the other way. And I really want to stress this. This isn't just a casual relationship. It's a hard and fast rule. For any ket vector you can possibly think of, like A, there is always 100% of the time a corresponding bra vector, A bar, that lives in that dual space. You can think of them as two sides of the exact same quantum coin.
Okay, so they're a pair. They're connected. But how? How are they actually linked together? Well, the relationship is governed by two very specific and absolutely crucial rules. These two rules are everything. Now, the first one, super easy, totally straightforward. If you add two kets, the bra that matches that sum is just the sum of the individual bras. No problem. But rule two. This is where the magic happens. If you multiply a ket by some complex number, z, the corresponding bra is not multiplied by z. No way. You have to take the complex conjugate. The bra becomes A times z star. And that little twist, that's the secret ingredient for this entire beautiful system.
So, we've laid all the groundwork. We get the idea of duality. We know the rules that connect these things. Now it's time for the payoff. Let's finally solve the mystery of where those ridiculous names came from.
All right, so here we have our bra vector, B. Now let's just see what happens when we invite its partner to the party. We bring in a ket vector, A, and we just slide it right next to the bra. We get this complete expression, BA. I mean, just look at that. See how perfectly they fit together? And as our source material so elegantly puts it, we do this to form brackets or brackets. And there it is, bra-ket, bracket. It's not a random name at all. It's a brilliant, descriptive, and let's be honest, a gloriously nerdy pun cooked up by the legendary physicist Paul Dirac.
But here's the thing. This is so much more than just a clever pun. This combination, this bracket, actually represents one of the most fundamental operations in all of quantum mechanics. The inner product. You can think of it as a way of projecting one quantum state onto another, which is exactly how we do things like calculate the probability of something happening. The notation itself is the tool. It turns this abstract math into something you can literally build.
Okay, I know this has all been a little abstract, talking about vector spaces and duality. So let's bring this down to earth. What do these bras and kets actually look like when we're using real numbers?
So in the real world, a ket vector like A is usually just represented as a column of numbers, a column vector. And each of these little alpha symbols in there, those are the complex numbers that actually define the state of our vector.
So if the ket is a column vector, what about its dual, the bra? Well, its corresponding bra, A, is a row vector. But, and this is so cool, this is where it all clicks into place, look closely at the entries. They are not just the same numbers flipped on their side. Every single entry is the complex conjugate of the entry from the ket. This is that second rule, that little twist we talked about, made perfectly real and visible. The notation literally is the operation.
So let's just do a quick recap. Kets and bras are dual vectors. They're two sides of the same quantum coin. Their relationship is just like the one between complex numbers and their conjugates. You put a bra and a ket together and they form a bracket, which is this really elegant notation for an inner product. And when you write it all out, kets are column vectors and bras are row vectors made of their complex conjugates. It's just a perfectly complete and beautiful system. And that really brings us to a final thought here. This bracket notation, it isn't just a label. It's a tool. It's a piece of language that's so perfectly designed that it actually makes some of the most complex ideas in physics simpler and clearer. And it just makes you wonder, if a simple, clever piece of notation like this can help us unlock the secrets of the quantum world, what other incredible secrets are just sitting there, hidden in the language of science, waiting for the right words or the right symbols to make them